Hey everyone, welcome back to another lesson in Greenfoot. We have been working a lot with games lately. We made a nice, cool, like ocean sailing cannonball game, but I want to go back to simulations for a bit, and I want to talk about one of the most famous simulations in that I well certainly that I've ever heard of, and this is called the Game of Life. So in 1970, a mathematician by the name of John Conway developed what he called a cellular automaton that was called the Game of Life, and simply it's just been called Life. Now, we're going to make the original Conway's Game of Life simulation. There have been many that have been done since then with greater variety and different rules. And in fact, my what we call a capstone at my university for mathematics was a group of me and three other people. Three people and myself, I should say, we developed a different version that involved cellular mutation and evolution and things like that of the different cells as they develop different strategies of life. So it was an interesting experience. It took all semester. But we're going to start with a simple one here, and I hope you enjoy it. We're also going to get to learn a lot about just more control of cells and accessing things in different places. When I say cells here, I mean cells in the Greenfoot. So hopefully you'll learn more about Greenfoot, but you'll also learn a little bit about Conway's Game of Life. Anyway, enough of an introduction. Let's get started. So for this project, we're going to follow these rules. So let me just go ahead and post them on. I want to post them over here on the Paint so I can talk about them. So the rules are basically this: that for every generation or iteration, if you will, each iteration of the game was in the game is called a generation. And it is called a game, by the way. It's called a zero-player game because once you set up the game, and the game is different depending on how you set it up, then you just let it go, and it plays by itself. So the rules are this: any living cell with two or three live neighbors will stay alive. Any dead cell with exactly three neighbors will come alive at the next generation due to reproduction. Any live cell, though, that has fewer than two neighbors will die because of underpopulation, and more than three neighbors will die because of overpopulation. So let me kind of draw that out right quick. Actually, I think I have over here on my notes. I definitely have a few examples. Let's take a look at this one here. So our cells are going to be the cells defined in Greenfoot. So I've got this here. Let's say that I'm looking at this cell in blue, and we'll come back to this diagram later, I'm sure. But in this cell here, what if I was counting their neighbors? We're going to count them, anyone that's at all adjacent to them, even catty corner. I would say this cell here is on a live cell. That's what the A is for, and it has 1, 2, 3 neighbors. So because of that, this cell is going to stay alive. Okay, and we could, if we had one more A here, then this cell would die. Now this D here is on an edge, so I don't have anything over here. But if this cell were, this cell has 1, 2, 3, 4 neighbors. Actually, it won't stay alive. What am I talking about? This blue cell has 1, 2, 3, 4. It would die on the next generation. So the next generation, this one would be dead. And then once it's dead, it's gonna stay dead until these change as well. So let's go. Let's keep going. We'll go over the rules some more as we go on. So basically, those are the three rules, though. Let's go ahead and get started and make a cell class, and I'll come back and give more details about the living situation in just a minute. I'm gonna make a cell class here, and we're gonna use. Let's see here. Let's see what we got. Some objects here. Well, we could use that marble. I think it worked pretty. It works well with this red dot. I know. I thought there was like a blue. Oh, there's like a purple marble you can use. Oh, there's just a blue dot right here. You can use that. Any of these are going to be fine. To tell you the truth. So I'm going to call this cell because that's what it is. They're called cells. And we'll go to our cell class, and yeah, that's good. I want to extend actor. And I'm going to make some instance variables. So public Boolean alive, and, oh, not public, I'm sorry. We don't make our fields public. Private. I was looking at the method list. Private Boolean will die. Private Boolean will live. And I'm going to make it have a couple different images. Greenfoot image. Live image. I need to make that private as well. And private Greenfoot image, dead image. So the idea here is that we're going to have several different ways that a cell can be. A cell can be alive and will die in the next before the next generation. See, all the deaths occur like in between frames, if you will. And then it could be dead and will come alive. It could be alive and will keep living. So lots of different things that can happen there. So I actually need Booleans to represent not just the state of whether you're alive right now, but what your state will be. And we're going to have a live image, which is just going to look like itself. And we'll have a dead image, which I'm just going to leave blank. Some people make them like a circle. It's colored in when you're alive and not colored in when you're dead. I'm just going to leave it blank. We could also color the entire cell with like a square, but I think the circle is going to work really just fine, okay? So we need a constructor. So right now, remember, Java makes a constructor for you. It makes public cell that calls super, okay? Well, we're going to change this. We're going to take some parameters. First parameter I want to take is a Boolean called alive state and an int called cell size. So I want to be able to control this game. I want to be able to make the, maybe we're going to run this experiment with 1,000 cells, so I need to make the dots really small. Maybe we're going to make it with only 20. So I'm going to include cell size, and that's something we're going to do a lot going on. Okay. So, pardon me for consulting my notes here. Make sure I'm not skipping anything. Okay, so we're going to go ahead and set the variable alive to this alive state. Remember, the call to super has to be the first line of the constructor. So we are calling super. You can leave it off and it'll be there, but I like to show it. And let's see here. We're gonna be able to set whether or not it's alive based on that alive state. Will die and will live. We're gonna set those both to false. Or maybe I can set will live to true. I'm not sure, but we'll say false. So in its current state, it is unknown what this one's going to be. It does not know what its future holds, but we're going to calculate that, so that's okay. Now, what I want to do is I want to create some images. We're used to like giving it, like we gave it a circle image here, but I want to manipulate that image. I want it to be shrunk or enlarged based on the cell size so everything fits nicely. So first I'm going to get a live image, which the way you get it is just get image. Now the get image command, which is in the actor class, when we bring up that documentation, you can see get image returns Greenfoot image. That's why I had to type it right here as Greenfoot image. That's my live image. It's just going to get its image there. Now the dead image, now check this out. This is going to be a little bit different. The dead image is going to be a new Greenfoot image, and I'm just going to give it blank. And what we're going to do is we're going to give it a size. So typically the new Greenfoot image command is used to create like a palette, and then there's the image class in Greenfoot has a lot of methods for like drawing rectangles and lines. So basically it's like a paintbrush palette, but we're just going to leave it blank. And then so that's going to be the correct size. It's going to be the size of cell size by cell size. The problem is my live image is too big, possibly, or maybe too small, depending on. So we're going to scale it. So we do live image dot scale, and then I give it an X and a Y, and so that's going to shrink or enlarge my picture as necessary. I think we saw that with the cannonball. We did that. So that's giving us a little bit of image manipulation. I don't want to have a bunch of different types of images and pick my image based on how big of a game of life I want to have. I want to be able to shrink it down. So that work is done there. Now we need to choose one of these two images. The default is this image we selected over here, this blue dot. We need to choose one of them. So the way in the actor class, they do have a get image. They also have a set image. And this set image is nice. I've used it to like animate, you have one image and then another image that looks like their feet are running or something like that. But we're going to use it just this way. We're going to set their image to the dead image if they're dead and the live image if they're alive. So I'm going to say if alive. Alive is a Boolean, true or false. It's true, they're alive. Then I'm going to set image to live image. Else, they must be dead. I'm going to set image to the dead image. Okay, I think that's finally done. That's a big constructor. That's a lot of work in that constructor, isn't it? All right, let's take a look now at the methods that we're going to write for this class. So the first one I want to write is public void die. And I'm not actually sure we're going to use all of these methods, but I want them out there to support in case we want to go back and add some more code. But most of them I'm pretty sure we're going to end up using at some point. So if you die, you are no longer alive. So alive equals false. So that's how you die. Public void, and then I'm going to mark for death. And I'm going to set will die to true. You are marked for death. I don't know why I find that funny. I just do. Got a little bit of a morbid sense of humor, ladies and gentlemen. Just a little bit. All right. Now I'm going to say public void mark for life. And I'm going to set will live to true. All right, next we need to do. Let's write some accessors for those. We got abilities to set them. We need to be able to access them. I'm gonna say public Boolean. Are you marked for life? Marked for life. So we have marked for life that marks you, and marked for life tells you whether you are. And we'll just return will live. And then from now on, if I don't know if this cell's gonna keep living, I can just call that marked for life. And I usually like you know me, I like to use methods, right? We'll see if we're marked for death. I don't like to use Booleans variables unless I absolutely have to. Return will die. All right. Next, let's do public void come alive. So what does it mean to come alive? Well, if it comes alive, that means that we're going to set their alive variable to true. And we're going to will die. We're going to mark them. We're going to say will die is false. And we're going to set their image to the live image. So that's what it means to come alive. You set your alive to true, you set will die to false, and you set your image to the live image, right? So that's what it means to come alive. Well, what about die? Did we, you know what, if you die, I think we need to, yeah, we need to go back up to that. Our die did not get fixed. Does everyone see that? We forgot to do the set image. And when you die, we have to set your image as well. So your alive variable is false, and we're going to say set image to dead image. There we go. Okay. Yeah, it's right there in my notes, and I just skimmed right over it. It doesn't, here it is. I'm trying to really plan, trying to give a good lesson here, and I can't even follow my own notes. Okay, we've got, I think we're missing an is alive. Let's do that. So public, we need some accessors. I just, even if we don't use them, I know we want to have access to them. So we're going to return alive and public Boolean is dead, I'm going to say return not alive. So it'll return true if not alive is false. So, I mean, if alive is false, not alive will be true. So, so I think we've got all these different ways that we can, look at our different and interact with our different cell. We're going to like that method about marking for life, marking for death, knowing if it's alive, knowing if it's dead. That's what's going to be really important to the logic that we do. Okay, so now we're ready to do the most difficult part of this entire simulation. Public int get living neighbors. Okay, so the actor class has a get one object at offset, and that's what I want to use. And the get one object at offset takes a dx and a dy. Dx means change in x and change in y. So we have to tell it, relative to where we are, where to go. So let me pull up that image again that I had before. So from this marked colored A, if I said, let me type in here, if I said get one object at offset, and I'm going to say, if I say -1, comma -1, and then you give it the class as well, comma, what is that class? It's cell.class. Then it's going to return to me, this one right here. That's going to point to that one if I'm calling it from this blue space here, because that's -1 in the x direction, -1 in the y. Remember, this, it's always backwards as it is in math class. We think y's go up and down. They don't. We think y's go up. They actually go down. This is positive for y, and then this is positive for x going to the right. So that's going to return a cell to us, and we're going to have our entire game is going to be completely full of cells. So it could return a null meaning nothing, but only if it went outside of the bounds of the game itself. Like we were on the far left edge and it went out of bounds, then it would not do that. But otherwise, we will get a cell. Okay. So we got to do that. Now, how many of these neighbors do we have? We have 1, 2, 3, 4, 5, 6, 7, 8. Oof. That means I got to call this 8 different times, right? You're thinking, no, I don't. Well, you're right, I don't. Let's call this x, and let's call this y. And let's loop from x equals -1 to x equals +1. And we'll also loop y's from -1 to +1. Pretty neat, huh? One thing we're going to have to be careful about, though, with this method here, get one object at offset, I want to say it will actually return itself if you give it 0, 0. So I'm going to want to skip the point where x, because when x goes from -1 to 1, x could be 0 and y could be 0. I want to skip that. So notice how I do that in the code, okay? So here we go. We're going to count them all up. First, I need a variable to count with. So I'm going to say int count, and it starts at 0. I'm going to do a loop. I'm going to say for int x equals -1. I want you to run while x is less than or equal to +1, x plus. Now I also need a loop inside of that for the y's. Int y equals -1, y less than or equal to 1, y plus. All right, I think it's worthwhile for us to talk a little bit more about that. Let's take just a second to review how this loop's going to work. I'm just going to get a fresh picture, because I have definitely marked all over this one enough times. I'm going to leave my rules up there, though. So we're going to start with x and y at -1. And what's going to happen is when you look at the loop, let me pull that over as well. And I know it's got an error in it right now, but I'll fix that in a minute. So when the loop starts, we're going to start with x equals -1. So that's going to be starting right here at this far left portion. Again, I'm saying pretend we're at this blue cell here. And then I'm going to set y to -1 as well. So that's going to be, so the y's are going up and down, the x are going left and right. So that's going to be this square right here. And what's going to happen is we're going to do this code, and we're going to do it for the y's before we ever change the x. Because this loop here is completely inside the loop for the x's. We're going to start with y equals -1. Then y is going to become 0, which means this cell. And then y is going to become 1, which means, oh, I'm doing it backwards. Sorry. We're looping with y's. So y's are going to become, we're going to start at 0, -1, -1. Then we're going to stay at -1 the x. We're going to stay back to the left at -1, but the y is going to change to 0 down here. Then the y is going to change to positive one, so it'll go here. Then after the y has gone from -1 to 0 to 1, finally y will become a 2, which makes this false. Then x will move up finally from -1 to 0, and will be here because y will start back at -1. So we'll be at 0, -1. And then we'll be at 0, 0. And we're going to want to skip that one. Then we'll be at 0, 1. Then the x will change finally to a 1. And y will be back at -1. Because y is going to start this loop over every time. Then y will go to 0. Then y will go to 1. So that's the order in which this is going to happen. All right, so I need to close that parenthesis, though. It's going to get mad at me. All right. So what I want to do is I want to get that object. So I'm going to say, now this method here returns get one. It returns an actor. So get one object at offset. So I need to say actor. But instead of doing that, what I'm going to do, because I want it to be a cell, I'm going to say cell. I know it's confusing. Lowercase cell for the variable name is assigned get one at offset x comma y comma cell dot class. All right, but that's going to be an issue, and it probably will get mad at me. We're going to see what's going to happen. Get one at oh, it's get one object at offset. Why'd they have to say that? Get one object at offset. So the problem with this is, it says Greenfoot actor cannot be converted to cell. That's the problem. But if I force it, it will. So I can do what's called a casting. And that's where you put the type that you want in parentheses. But it needs to be a subclass of what this returns. This returns an actor, because cell is a subclass. I can force it into there. It could cause a runtime error where the program breaks, but only if for some reason it returns something that wasn't a cell. But it will return a cell. I know that because of that code right there. And I had to do that because I need this cell's, I need access to its methods. Okay, so we are going to call we're going to call a method, and we're going to say if cell dot is alive, then we're going to increase our count. This is close to right, by the way. We need to make some edits, but I just want to start with this. So notice that is alive is a method that is inside the cell class. So you might think that I could just say is alive because I'm in that class, right? We've said that. But that would be telling me, going back to this example here, that would be telling me whether this blue cell is alive, which is information I might need, but it's not, that's not the one I want to know is alive. So if you're trying to call a method, even if it's in the class you're working in, from an object that's not the object you're coding for, you need to call it on a different instance of that class. So I'm calling it not on this cell, I'm calling it on that cell. So cell.isAlive. But we need to be careful for a couple more things. We're going to fix this up just a tiny bit. First of all, I don't want to do this on myself. I'm not supposed to count myself as a living neighbor. So I'm going to say if x does not equal 0 or y does not equal 0. That exclamation mark equals means not equal. And the double vertical line means or. So what I'm saying is as long as one of those is not 0, I could have also said, if not, x equals 0 and y equals 0. But I'm trying to find a way to avoid when they are both 0. Because if they are, I want to just skip over that. The next problem is that occasionally we could be on the far left corner. So here, let me show you another example. So, like, what if we had a situation kind of like this? So we're on the edge of the world. Well, if I try and look for my neighbors over here, and over here, they're going to actually return null. It's not going to cause an error, but it will return null. And if you try and call a method on a null object, then you get what's called a null pointer exception. Exception means error. So that we need to make sure that it's not null. So I'm going to say cell does not equal null, and okay, so there's a lot to unpack here. The and symbol has what we call a short circuit nature, because if I say false and, it doesn't matter what I say at the end. I can say false and false, it's false. False and true, it's still false. So in Java, when the first thing is false and then followed by an and, it will ignore this code, which is good, because I don't want it to say cell.isAlive if cell is null. If the cell were null, because I only want it to do this if the cell's not null, right? So if the cell's null, this would cause an error that would break my program. So I wanted to avoid that, and that's why I do that. And that's a little easier than having to say if cell equals, if cell does not equal null, and then inside that put another if statement, which I could certainly do. All right, so there it is. We check to see if it's null. If it's not null, we go ahead and check if it's alive. If it is alive, we'll go ahead and up the count of our object. Be advised that if I had put this second and this first, that would be a problem, because it would do the thing on the left first, and that could cause me a null pointer exception when I'm on the edge of the world and looking to the left and there's nothing there. Okay, so all right, we got all that, and we're counting everything up, and I think that's about it for this method. So we just need to return that count. So that's just going to count the living neighbors. All right, but it's time for the act. Finally, I bet you're wondering, when are we going to do that, right? Well, what do you do? Well, with the act, we're going to just, it's really simple actually, very short. We're going to say if is alive and marked for death, then we're going to die. If you're alive and you're marked for death, you need to die. All right. Else, if you is dead and you are marked for life, I want you to come alive. That's pretty much it. Okay. All right. Now it's time for us to write the My World class, and we're going to give it a good name. We're going to give it the name of life. So let's go here. And we're going to change this name from My World to life. And we'll have to change the constructor, because the constructor has to match the name of the class. All right. Now, with this life world, we're going to be using cells, right? We're going to be, we could start with a 200 by 200 by 3. That would work. Might want to, it's alerting me that I've erased a file because I changed the name of a class. Let's go ahead and do 200 by 200. But I really want you to go in there and see how this works by making that a smaller number. So we'll come back to that. But I want it to look cool and impressive. And I'm going to do 3 by 3. So there will be 9 total pixels per cell. It'll be a 3 by 3. Remember that our images will be scaled appropriately. So they'll be scaled by cell size, comma cell size. So it'll be a 3 by 3 picture. All right, we're going to make some methods here. Let's make public void make grid. And I could put this in the constructor, and then every time you restart the program, it will automatically make a different grid. But I'm actually going to want someone to have to call this method, because I want it. That is the important part. The making of the grid is what sets up everything. That from that point, the game is a 0-player game. So how are we going to do this? Well, we need to loop through the entire grid, and we need to set some of the cells to be initially alive and others to be initially dead. So I'm going to do that. I'm going to loop through 0 through the width of this cell. So if we have 200 by 200, that means our x's will go, our cells, each x and y value is a cell number. Our cells for the x will go from 0 all the way up to 199, which is 200 cells, but we start at 0 count because computer science. All right, so I'm going to say for int x equals 0, x less than get width. Okay, I don't want to put in the 200 here. I almost did it, but I want to be able to go back there later and change this and have this get recalculated. And as long as I say less than get width, it will not actually reach it. It'll go to get width minus 1, and we'll increase by x. Then I'm going to say for int y equals 0, y less than get height, because y's go up and down, y plus plus. Now, inside this loop, what we're going to do, understand this is going to loop through the entire grid. The x is going to start at 0 and the y is going to go straight down, okay? Then the x go to 1 and the y is going to go straight down. So it's going to go through this entire grid and populate every single one of these cells with something. I want to make it a 10% chance, I think, but we're going to use, excuse me. We're going to make some static variables today. And in fact, I'm going to do that here with this 200. That wasn't good. It bothered me. I did that anyway. So we've already talked a little bit about static. We know that static allows you to call it without making an instance of the class. Well, there's another thing you can do. Because the super constructor has to be the first line of code of a constructor, I am not allowed to set any variables before that time. But it's a very good idea to have variables. Otherwise, people look at the 200 and the 3, and they have no idea what it means. And we hate that. We call them magic numbers. But we're going to make some constants. Constants are values that you're not allowed to change. So check this out. Because they're constants, I'm also going to make them public, which is weird. But we make our constants public. If you don't, it's okay. But we usually do. And I'm going to put the word static. Static is done before the creation of any object. We saw that the other day with BlueJ. That you could run a static method before you made an instance of the class. So I'm going to say public static final int, and I'm going to say width. And then I'll say 200. Then I'll say public static final int height 200. And then I'm going to say public static final int cell size, and I'll say 3. And so now I'm going to use these methods here, and this is really convenient because then later on when I want to change the cell size or I want to change the width or the height, I don't have to go scrolling around to find it. It's right there at the top of my method, and they're constant. So if I try and do something like this, like hey, let's increase width by 1, you're going to see I'm going to get a big fat no, cannot assign a value to a final, right? So it's just a way, again, of making sure I don't mess up. And because I can't change it, there's no problem with making it public. I can't change it outside of the class somehow. That means it's just I can find it anywhere I want. The word final is what makes you not be able to change it. The word static means it gets done before the constructor, along with some other things. And also, I'm allowed to assign it a value here. And I need to because it happens before the constructor, so there's no other time for me to assign it. So kind of weird. You're not used to assigning variables values up here where you're declaring them, but we're going to do that with our final constants. And so now that's going to work. Okay. All that being said, okay, I'm going to make one more constant, which is what got me up here to begin with. I'm going to say public static final double, and I'm going to call it life, or how about this, initial, or init, life chance. So I'm going to want to see what happens when we start with different populations. We're going to start with the initial chance of you being alive, but only 10%. And maybe even comment that. 10%. All right. Okay, so all that. No, you know what? I don't want to do 0.1. Let's do 10. Let's just do 10%. Sorry, I know I keep changing everything. We'll make it an int too. Because here's how I'm going to do this. I'm going to get whether or not it should be alive. Boolean. Make alive. Equals Greenfoot dot get random number. This is a static method in the Greenfoot class. To find it, you have to go to Help, Greenfoot class documentation, and there are all sorts of helpful things in this Greenfoot utility class, and they're all static, which means you don't have to make an instance, you just call it. That's where you get your keyboard information, that's where you get your mouse information, all that kind of stuff. What key you press, you make a prompt, all sorts of things. Change the speed, play a sound, you name it. Start the animation, stop it. Really an important class, and they're all static. So you just say Greenfoot, and I'm say Greenfoot.get random number, and I'm going to put a 100. It'll return a number from 0 up to, but not including 100. And I'm going to say less than init life chance. So how many numbers are less than 10? If you pick a random number from 0 to 100, well, you got 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So there are 10 different numbers that could be out of the full 100 numbers that we're going to choose from. And so it's going to evaluate this first. That will either be true statement or a false statement. If it's true, make alive will be true. If it's false, make alive will be false. All right, let's construct our cell. So I'm going to say cell C equals new cell. And remember, we're going to take in our cell constructor needs to take in is it alive or not and the cell size. So I'm going to say is it alive, make alive. That's what they're value. And I'm going to call it get cell size, which is the method that returns the cell size of the world. I could have also used my constant there, but I wanted to introduce you to that method from the world class. The world class has a get cell size, has a get width, which we use here, and has a get height. So yes, I could have used these static methods, but I just didn't. Okay. Now, those static variables. Now we need to assign it. So we're going to say add object, and the add object method will take, I can't remember the order. Is it the location, then the object, or the object and the location? It is the object and then XY location. So the object is C, the cell, and the XY location is what? Well, remember our X and Y is looping through all the different cells. XY is our location. All right, so that is done. We have made the grid. Now we're going to do something you probably are going to be a little surprised about. You should know at this point all about the ACT method for the actors, but did you know there's actually an ACT method for the world? There is. The ACT method for the world is called before any other ACT method. Check it out. ACT, right there, ACT method for world. This method is called before it calls any of the other ACT methods from any of the other actors. So this is where it's going to allow us to calculate who needs to come alive and who doesn't. And remember that cells ACT method, all it did was set them alive or not. So this is actually where most of our our decisions are going to be made about who's going to live, who's going to die. Once again, though, we need to loop through stuff. So we're going to need to get all of the cells in this game, and that's a method. In the world class, check it out. It says get objects. Notice that it takes in a class that you want the objects to be of type, and look what it returns. A list of the same type that you give it here. That's what that bracket A is saying, okay? So we need to import java.util.list. Okay. And I'll say list. What's my list going to be? Of type cell. I'll just call it cells. And I'm going to say get objects of what class type? Cell.class. And it'll return all those objects. Okay? Now, and notice they'll be typed as a cell, so that's actually kind of convenient. And now we're going to loop through every single one of those. Now, the cells are going to be like this. So we're going to have, I still want to leave those rules so we can take a look at it here, because we're going to need it. But the way this is going to work, we're going to have an array, a list, and we're going to have different cells sent to us, okay? So we'll have like a cell here, and another cell, another cell, another cell, another cell in our list, right? It's going to be a huge list, as long as we have width times height. If we have 400 cells, it's going to be 400 different things in this list. The first index in a list, just like an array, is index 0. So that's index 0, that's index 1, that's index 2, that's index 3, all the way down to the very, very end. And the last element in an array list or a list is size minus 1. So, for example, if I have a list of 10 items, the indices would be 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. All right, let me show you how that works. Okay, so I'm going to do a loop here. I'm going to say for I int I starts at 0, I less than cells dot size. Cells dot size. Okay, so I less than it. So remember I said that if I have if I have a list of 10 items, okay, the last index is 9. That's why I have to say I less than, not less than or equal to. I'll say I plus plus. And here's how you get the cell at that index. So I'll say cell, I'll just call it cell, equals cells dot get I. So remember, every variable has to have a type. So this is a new variable. The type is of type cell. I'm calling it cell, which is confusing. And then it gets something from cells, the name of the list, dot get I. I can call that one anything. I could call it like X if I wanted to, but then it wouldn't make sense. Or maybe C for cell, but I'll just call it cell. But so the class type is cell. The variable name is lowercase cell. And it is going to be equal to the ith item from our list. And that's how you get an item from list. You say the name of the list dot get, and then you give it the index you want. Well, I'm giving it the index I, which means I'm going to get the 0, then I'm going to get the 1, then the 2, then the 3, then the 4, one at a time, all the way through the whole thing. Okay, so now that I've done that, I need to get their living neighbors. So I'm going to say int living neighbors equals cell dot get living neighbors. I think that's what we called it, right? I'll go back and check. Yeah, get living neighbors. So I'm calling that method on the cell, right? All right, now we go to our rules. Okay. Any live cell with 2 or 3 neighbors stays alive. But any live cell with fewer than 2 or more than 3 needs to die. So, or be marked for death. I'm going to say if cell dot is alive and living neighbors, what do we say, less than 3 or less than 2? Fewer than 2 neighbors. Fewer than 2. Okay, so less than 2. Or living neighbors greater than what? Greater than 3? More than 3. Okay. It needs to die at the end of this generation. So that means we're going to mark it for death. And each generation will be when we loop through all the cells and set them to alive or dead. So I'm going to say cell.mark for death. All right, let's do another one. Else if. So if that's not true, check this. We have another condition. Any live cell with 2 or 3 live neighbors stays alive. So I'm just not going to do anything to that. If it's alive and it fits those, then leave it alone. Any dead cell with exactly 3 neighbors comes alive at the end of the generation. So if cell dot is dead and living neighbors is equal to precisely 3, then we need to mark it for life. Cell.mark for life. And I call it marking because it doesn't actually come alive until the generation is ready. Okay. Oof. I think we're done. It's probably going to be some debugging, right? Okay. Mark for life, right? Mark for life. All right. Hopefully there's not too many bugs and this works the way it does in my head. All right, so we've got our world here, but nothing's there. Let's right-click on it and make grid. Okay, I've got a bunch of little dots everywhere, and those are the cells that are alive, right? Well, let's run it and see what happens. Okay, so things should start changing. Oh, I've had a massive die off. And okay, we got some life coming back here. Now, I want you to go on Wikipedia and research Conway's Game of Life. You're going to see that there's lots of different like theories about what happens. There are things called like travelers or UFOs that will like fly across the screen. And here, this is a pop. Look at this little square formation here. It's blinking back and forth, oscillating. Things are going to migrate in and start making bigger and bigger areas. Now yours probably looks quite a bit different than mine because of it was random how it's set up, right? All right. Well, that's pretty cool. Oh, this is a solid state. Once they're in that little football shape, they don't change, and they have names for all these different things. All right. So I'm gonna pause that. I'm going to go into this, and if you want to just see one generation at a time, just hit Act. Just hit the Act button. You'll see it progress just one at a time. I'm going to go in here to my life, and I'm going to change a couple of these static constants. I'm going to make this 20 by 20 with a cell size of 50. Hopefully that doesn't make the board too... Ugh, it's a little big. Okay, hold on. Let's do a cell size of like 40. It's 40 by 40, you know, so it gets pretty... Okay, no, all right. 35? All right, that's good. All right, let me make the grid. So this should allow us to see a little bit more what's going on. It's not going to be that pretty, you know, impressive beginning feature, but... Oh, I don't know. That is pretty cool, though. So I think that's settled into a... That's definitely settled into a kind of a default arrangement. Now, if we go over here to the world and you right-click on it to set images, there are some that you can actually set to kind of see a grid. It doesn't work perfectly. You have to scale it, but if you go to backgrounds, you can kind of select them, and you have to play with it and get the absolute right. See, let me see if that's the right settings. Or otherwise, look, yeah, see, that's not quite right. But it gives you, if you give it the, I want to say it's pretty much right at 10 by 10 with a cell size of 50. And I do that so that you can kind of see that offset. Okay, so here, this cell here has got no living neighbors. This cell here has 2. This one should stay alive. So we see it. Oh, and all that came back were these 2 here. So this one here's got 1 living neighbor. It's going to die. This one here's got 1 living neighbor. It's going to die, but this one's going to stay alive. Oh. Oh no, this one had 2 living neighbors. I'm sorry, I forgot. You count the diagonal. So it had 2 living neighbors. And so this cell here that was dead had 1, 2, 3. So it's gonna build up. But that's it. That's a stable system. That's equilibrium. Nothing's gonna change there. So yeah, that's the settings. If you want to really understand this code, it's 10 by 10 by 50. I'm not gonna do that though. I'm gonna do 200 by 200 by 3, and I'm gonna start with a 20% chance of life because I want to see it. And I'm going to take this set image, play with the background anytime you want. I don't care. You can make it a crumple up piece of paper, stars. I don't know. I'll do this little thing here. The background's cool. Also, play with that image. That's a pretty boring cell image, right? Make it something cool. Oh, I forgot to make the grid. Right click on the object to make the grid. Should take a second. There it is. Because it's looping through a lot of cells, isn't it? All right, so a lot more alive in my initial stat here. I don't know what difference that'll make so much. As I watch. Ooh. Well, I hope you enjoyed this. I am going to attach some instructions. They don't have the code, but they explain like what we did and why we did it. So I'm going to attach that to the assignment as well. And just if you want it for an added reference, you're going to make something for a project that uses this offset counting, but and uses the grid nature of Greenfoot. You're going to make the game of Go, and I'm super excited to play it, especially to see the customizations that you do on it. So you're going to have a few days where you work without a video. So I'll see you when I see you.